Welcome back. This time we'll talk about the joy of algebra. Now, I think the first time I experienced the joy of algebra was when my father asked me to solve the following problem. He said, okay, Art, I'm going to teach you algebra. 1q plus 1q is 2q. And 2q plus 3q is 5q. Now you tell me, what's 5q plus 5q? And I thought for a moment and I said, 10q. And he said, you're welcome. Anyway, that was my first experience in experiencing the joy or the groan of algebra. In this lecture, we will learn to use algebra to explore mathematical magic tricks, how to do amazing mental calculations, how to solve linear equations, and even how to understand some of those dreaded word problems. The second time I experienced algebra was in trying to understand the following magic trick. Now, you have to all promise to do this right now, okay? I want you to think of a number between 1 and 10. All of you out there, think of a number between 1 and 10, okay? Double that number, all right? Now add 10 to whatever you're thinking, okay? Divide that by 2, and now subtract your original number. Concentrate on the digit, the number you're thinking of now. I'm getting the number 5. Is that what you got? Okay. So let's see how this magic trick works. I think this is the best way to introduce algebra. Okay? So algebra is all about assigning letters or variables to unknown quantities. Okay? So when I ask you to think of a number between 1 and 10, I don't know what that number is. Let's just call that unknown number n. N as in number. Okay? Now, what was the first thing I asked you to do? I said, double that number. So you're taking n plus n, and we know from my father that 1n plus 1n is 2n. Okay, and by the way, we write that as 2n. We don't write 2 times n, because then it would look like a 2xn, and x we're going to save as a variable for later on. So we just write it as 2n. We don't have the multiplication sign. Okay, then what did I say? I said add 10 to it. So if you have 2n and you add 10, then now you have the algebraic expression 2n plus 10. What was the next thing I asked? I said divide that number by 2. So you have 2n plus 10, dividing it by 2, that gives us n plus 5. You see why that works? If I were to multiply 2 times n plus 5, then we would get 2n plus 10. Okay, so 2n plus 10 divided by 2 is n plus 5. Finally, I said subtract your original number. Well, what was your original number? I didn't know what it was. I called it n, right? So you have n plus 5, and when you subtract n from that, you are left with 5. Okay? So that, I think, is the best way to understand algebra. Now, if we were to follow this up with another magic trick, okay? Here's algebra lesson number 2. Okay, again, I want you to think of a number. Now, this time I'm going to need somebody from my audience here. So I want you to pick a number between 1 and 20. Okay, let's say 9. Okay, we'll put that on the first line. Okay, and now someone else, give me another number between 1 and 20. 2. Okay, so we have the numbers 9 and the number 2. Okay. Now I want you to, we're gonna pretend like we're Fibonacci here. Okay, we're gonna take the numbers 9 and 2 and add them together. That puts us in row 3, and 9 plus 2 is 11. Okay, now next we're gonna take 2 plus 11 to get 13. Then 11 plus 13 we get 24. We see we're being like Fibonacci here. We're adding two numbers in a row to get the next number. 13 plus 24 is 37. 24 plus 37 is 61. 37 plus 61 is 98. 61 plus 98 is 159, and 98 plus 159 is 257. Okay. Now, with a calculator, I want you to now add all the numbers from row 1 through row 10. And I can tell you, just by looking at that chart for one quick second, that the total is going to be 671. That's right, isn't it? Okay. I'll tell you how I did that later, but here's the next magical surprise. I want you to now take the number that you have in row 10, divide it by the number that you had in row 9. Now, I had no influence on the numbers that you started with. You could have picked any two numbers. All I really wanted was positive numbers anyway. Divide row 10 by row 9 and give me the first three digits of your answer, including the decimal point. What do you have? Let's see, row 10 over row 9 here with 257 over 159. Hey, we get 1.61. If you were trying this at home, I want you to do the same thing. Start with any two numbers, okay? 9 and 2 is what we used here, but pick any two numbers at all and do the same process that we did, generating the numbers 1 through 10. When you divide the number in row 10 by the number in row 9, I guarantee that the first three digits that you get will be 1.61. And I'll explain why that works later. Okay, if you were to continue this process, by the way, if you were to, instead of stopping after 10 rows, you were to go to, say, 20 rows, okay? I don't recommend you do that, but if you do, and you divide, say, the 20th number by the 19th number, or the 43rd number by the 42nd number, those ratios are getting closer and closer and closer to 1.618, our mystical friend, the golden ratio. Now, I won't explain why that part works, but I will explain the rest of this. Okay, so what's going on here? What's the algebra involved? Again, here we're dealing with two unknown quantities. I didn't know your first number, and I didn't know the second number. So let's call those unknown numbers x and y. Okay, those are very common algebraic variable names, x and y. So if x is in row 1 and y is in row 2, then what's going to be in row 3? Simply x plus y, okay? Now if we add row 2 to row 3, add those together, then we're going to have x plus 2y. And if you take row 3 and row 4, add those together, and just watch this carefully, x plus x is 2x, y plus 2y is 3y, so we have 2x plus 3y. Getting the hang of it? All right, row 4 plus row 5 is going to be 3x plus 5y. 2x plus 3y plus 3x plus 5y is 5x plus 8y. By the way, are you noticing the numbers that are appearing here? 3x plus 5y plus 5x plus 8y is 8x plus 13y, 13x plus 21y, 21x plus 34y. Look at the coefficients behind the x's. Look at the coefficients behind the y's. They're 1, 1, 2, 3, 5, 8. Who do you appreciate? Who can't you tolerate anymore? Fibonacci, right? Okay, so add those numbers together, okay? We've got, the thing I'd asked you to do is take row 1 through row 10 and add all of those together. Now, if you add all of the x's together, 1x plus 1x plus 1x plus 2x, 3x, 5x, 8x, 13x, 21x, we get 55x. And if we add up all the y's, we're going to get 88y. So the sum of all those rows 1 through 10, is 55x plus 88y. Now, does that look at all interesting to you? 55 and 88, what do they have in common? They're both multiples of 11. And therefore, we can factor an 11 out of that number. So 55x plus 88y is 11 times 5x plus 8y. Maybe it's easier to see that moving backwards, right? 11 times 5x plus 8y, as you move up, is 55x plus 88y. That's nothing more than the distributive law of arithmetic. But what's so interesting about 5x plus 8y? Well, if you look carefully, in row number 7, what do we have there? It's 5x plus 8y. So what am I doing when I'm looking at, just briefly, at that chart? What I do is I take a quick look at what's in row number 7. I see it's the number 61. I multiply that by 11, and that's going to be my answer. So 11 times row 7, 11 times 61 is 671. Now, some of you may be saying, well, that may be easy for you, Professor, but how am I supposed to multiply 61 times 11? Well, you've come to the right place. I'm going to show you an easy way to multiply any two-digit number by 11. Okay, so for instance, 61 times 11 is as easy to do as 6 plus 1. 6 plus 1 is 7, and that's your answer. 6, 7, 1. Just put the 7 in the middle. You see it? Here, let's do another example. Say the problem was 53 times 11. 5 plus 3 is 8. So what's the answer? 583. 583. Right, this you could teach a child to do it, which they feel very good about, by the way. They can multiply any two-digit number by 11. 81 times 11, right? 8 plus 1 is 9, so the answer is 891. Now, before you get too excited, I've only shown you half of what you need to know. Because what if the numbers add up to something bigger than 9? Suppose we had a problem like, 85 times 11. Now, 8 plus 5 is 13, and the answer, I'm afraid, is not 8, 13, 5. We only have room for the 3, but the 1 makes the 8 carry, and the answer is 935. All right, here you try another one. Let's say the problem was 77 times 11. 7 plus 7 is 14, so what's the answer? 847. Now, why this method works is easy to see if you look at some examples of how you would normally do 61 times 11 on paper, right? 1 times 61 is 61, 10 times 61 is 610, and when you add them, notice you have a 6 on the left and a 1 on the right, and in the middle you have the 6 plus 1. That's why it will always work. Similarly, with 85 times 11, we'd have an 8 on the left, a 5 on the right. The 8 plus 5 is the 13, and that's where the 3 goes there, and the 1 makes the 8 carry to get the 935. You're really doing it like you would do it on paper, but by doing it the way I've explained it to you, it goes a little bit easier in your head. Okay, let's get back to the magic trick. We now understand why the sum of those first 10 numbers is easy to obtain, right? That is, it's 11 times row 7. But how about that mystical ratio? Why did we get 1.61 when we were done looking at row 10 divided by row 9? This is all based on the concept of adding fractions badly, okay? How do you add the fraction 1/3 plus 2/5 badly? If you didn't think at all, I mean, how did you think fractions were going to be added when you first encountered them? You said, well, I'll add the tops together, I'll add the bottoms together, right? 1/3 plus 2/5 is maybe 3/8. Nice try. It's not the total, as we know. But what you might not know is that the answer you get when you add the numerators and add the denominators is always guaranteed to be in between the two numbers. Not necessarily halfway in between, but somewhere in between. So for instance, if I started with 1/3 and I added 2/5, then the number 3/8 must lie somewhere between 1/3 and 2/5. In general, for any positive numbers, a, b, c, and d, if I have the fraction a over b less than the fraction c over d, and I add the numerators and I add the denominators, then the number that you get, which mathematicians, by the way, call the mediant of those two numbers, then we're going to get a plus c over b plus d, and that is guaranteed to lie in between. And once you get a little more comfortable with your algebra, you could actually prove why that's the case. But just take my word for that for now. Okay, so what's the problem we have at hand? We want to look at the number in row 10 divided by the number in row 9. Now the number in row 10 is 21x plus 34y. The number in row 9 is 13x plus 21y. So we're interested in that fraction, 21x plus 34y over 13x plus 21y. Now that happens to be the mediant, the bad fraction sum of 21x over 13x and 34y over 21y, right? If I take those two fractions and I add their numerators and add their denominators, that's what I'll get in the middle. But what is 21x over 13x? Well, the x's cancel, right? If I have 21 times 7 over 13 times 7, well, that's the same as 21 over 13. So we get, on the left, we get 21 13ths, which is 1.615 ... On the right, we have 34y over 21y, and that reduces to 34 over 21, which, if you calculate it, is 1.619 ... And so what that means is, as long as your numerator and denominator was positive, what you have here is guaranteed to lie in between 1.615 and 1.619. And as you recall, I only asked for the first 3 digits of the answer, and that's why we are guaranteed to begin with 1.61. And if you were to do this farther and farther down, you'd actually get closer and closer to 1.618, but I'm not going to prove that here. So where does algebra come from? Algebra was the invention of an Arab mathematician named Al-Khwarizmi around 825, somewhere in the 9th century. He wrote a book whose name I will probably mispronounce. It says Hisab al-Jabr wal-Muqabala, which literally meant the science of reunion and the opposition, later on interpreted as the science of transposition and cancellation. That's actually the way I think of it. But this al-Jabr was having to do with the science of the reunion and the opposition. And al-Jabr is where we get the term for algebra. As a matter of fact, this was such a profound contribution to civilization that later on, computer scientists used the word algorithm as any formal procedure of calculating in a particular way. That's how it was named in honor of Al-Khwarizmi. As I said in the beginning, algebra is discovering the unknown, using variables to represent unknown quantities. So let's start you off with one of those dreaded word problems. Find a number such that adding 5 to it has the same effect as tripling it. Okay, I'm going to jump in with a word problem here. Find a number so that adding 5 to it has the same effect as tripling it. Okay, well, I don't know what that number is yet. Let's call it x. All right? And what do you get if you triple the number x? You're going to get 3x. 3 times x. And that's going to be the same thing as when we add 5 to it. So we want 3x to be the same as x plus 5. Now, if there's only one thing you remember from this entire lecture today, it should be this: the golden rule of algebra, which says, do unto one side as you would do unto the other. Okay? So I have 3x equals x plus 5. But I want to clean up this equation. So I will do unto the left side as I will do unto the right side. I'm going to subtract x from both sides. Okay? When I subtract x from both sides, I have 3x minus x equals x plus 5 minus x. So the left side, 3x minus 1x is 2x. And on the right side, x plus 5 minus x, hey, that's from our magic trick, is 5. So now I have a much simpler equation that says 2x equals 5. How do you solve 2x equals 5? Well, do unto one side as you would do unto the other. Let's divide both sides by 2. And when you do, you have, on the left side, you have x, and on the right side, you have 5 over 2. And therefore, you started with this complicated equation. You ended up with, well, the simplest equation of all, the answer. X equals 5/2, or 2.5. By the way, it's always a good idea after doing a problem like this to verify your answer, right? Let's see, 2.5, does that make sense? Well, let's see, if I triple 2.5, what do we get? 7.5. If I add 5 to 2.5, what do we get? 7.5. Hey, it works. That's nice. Let's do another problem. I claim out there exists a number such that if you double it and add 10 and then triple it, you get 90. Find the original number. Okay, again, let's call the original number X. What did I say to do with it? I said double it and add 10 to it, just like in our magic trick. So we have 2 times X when we double it, and then we add 10 to it. That's 2X plus 10. And then I said take that entire quantity and triple it. So I have 3 times 2X plus 10, and I said you were going to get 90. All right, that looks like a messy equation, but let's simplify it by dividing both sides by 3. When you divide the left by 3, you're left with 2X plus 10. Hey, did you get that? You're left with 2X plus 10? I just realized that myself. The right side, you have 30. Now, how do you simplify that equation? Let's get all the numbers on one side, right? What would you do there? Let's subtract 10 from both sides to get 2X equals 20. And now what do? Divide by 2, and you're left with X equals 10. All right, here's a word problem that has personal meaning for me. Today, Laurel is twice as old as Ariel. Okay, this is true. These are my daughters, Laurel and Ariel. 2 years ago, Laurel was 3 times as old as Ariel. Now the question is, how old are they today? So this time there are 2 unknown pieces of information, right? Laurel's age today and Ariel's age today. Let's call those L and A respectively. So what was the first thing I told you? That today Laurel is twice as old as Ariel. That means that L is equal to twice A. L equals 2A. Then I gave you a second piece of information. That is, 2 years ago, how old was Laurel 2 years ago? L minus 2. Laurel was 3 times as old as Ariel. How old was Ariel 2 years ago? A minus 2. So the sentence that I gave you translates into L minus 2 equals 3 times A minus 2. But 3 times A minus 2, that's 3A minus 6. So L minus 2 is 3A minus 6. So I've given you 2 equations with 2 unknowns, Laurel and Ariel, L and A, and these 2 equations. Well, let's substitute what we learned from the first equation. It says that L is equal to 2A. So I can replace L with 2A wherever I see it. Hey, I see it in the second equation. So instead of having L minus 2, let's turn that into 2A minus 2. And on the right side, we still have 3A minus 6. Okay, we got the L out of here. Oh, sorry, I didn't mean to say that. Anyway, got the L out of here, and you have 2A minus 2 equals 3A minus 6. Okay, what do? Let's simplify things a little bit. Let's add 6 to both sides. I mean, you can do lots of things here, but if we add 6 to both sides, that gets rid of the 6 on the right, giving us, on the right, we're left with 3A, and on the left, we have 2A plus 4. All right, now what should we do? Well, let's subtract the 2A from both sides. So on the left side, we have 4. On the right side, we have A. And hey, we're left with A equals 4. Therefore, today, Ariel is 4, and Laurel, being twice Ariel's age today, is 8. Incidentally, Laurel and Ariel really are the names of my daughters, but my wife is also a mathematician, and so people were a little afraid that we were going to give our children mathematical names, you know, like if it was a boy, add 'em, if it was a girl, subtract 'em. But luckily, common sense prevailed. Okay, the last technique I want to show you today is something called FOIL, okay, which is when we're multiplying several variables together. So for instance, suppose I want to multiply the quantity A plus B times the quantity C plus D. Let me first tell you the answer and then we'll explain it. Okay? A plus B times C plus D equals AC plus AD plus BC plus BD. So if you look at the first quantity there, all right, AC, that's what you get when you multiply the first numbers. And then AD is what you get when you multiply the outer numbers. And then BC is what you get when you multiply the inner numbers. And finally, BD is what you get when you multiply the last numbers. So we have first plus outer plus inner plus last. FOIL, that's why we call it FOIL. Now, why does FOIL work? It's nothing more than the distributive law. The distributive law says if I take A plus B times C plus D, well, we can look at that as A times C plus D plus B times C plus D, right? The distributive law says A plus B times X is AX plus BX, no matter what X is. Here, X just happens to be C plus D. So we have A times C plus D plus B times C plus D. But what's A times C plus D? By the distributive law, again, we get AC plus AD. And by the distributive law on the second term, we get BC plus BD. Hey, put that all together and we have AC plus AD plus BC plus BD. That's FOIL. You never have to go through that derivation again. You just know that it works. Let's do an example to solidify that. Suppose we wanted to multiply 13 times 22. The way you actually do multiplication on paper is really nothing more than an application of FOIL, the distributive law. That is, 13 is 10 plus 3. 22 is 20 plus 2. If you multiply them together, you have 10 times 20 is your first term. And then let's see, outer would be 10 times 2. And then your inner would be 3 times 20. And then your last would be 3 times 2. So we have 200 plus 20 plus 60 plus 6, which is 286. Okay? We can use FOIL to do other kinds of multiplication. We're going to multiply x plus 3 times x plus 4. Multiply x plus 3 times x plus 4. If you multiply those first two together, you have x times x, which is what? X squared. Right? That's the definition of x squared. It's x times itself. Then we have the outer, x times 4, which I'll write as 4x. And then we have the inner, 3 times x, which is 3x. And then the last terms, 3 times 4, is 12. Add those all together, we have x squared plus 4x plus 3x plus 12. But 4x plus 3x we know is 7x. So when you multiply all that together, you have x squared plus 7x plus 12. Here's another example. Suppose you were to do x plus 6 times x minus 1. Maybe you want to think of x minus 1 as x plus negative 1. Okay, so FOIL still applies here. X times x is x squared. And then x times negative 1 is negative x. 6 times x is 6x. 6 times negative 1 is negative 6. Add those all together. What we are doing now is called combining like terms. We have 6x minus x. That gives us 5x. So that's x squared plus 5x minus 6. Last example, if you take x plus 3 times x minus 3, then when we do the first, we get x squared. When we do the outer, we get minus 3x. When we do the inner, we get plus 3x. And when we do the last ones, we get minus 9. Okay? The minus 3x and the plus 3x cancel, completely annihilate each other, and we're left with x squared minus 9. That is, x plus 3 times x minus 3 is x squared minus 9. And you can see, going through the same kinds of calculation, that if you take x plus y times x minus y, multiply them together, you get the expression x squared minus y squared. We'll see applications of that last equation in our next lecture. But let me recap what we've learned so far. In this lecture, we've used letters, variables, to represent unknown numbers. We've learned an amazing way to multiply by 11s. We've started to see how to solve word problems, how to solve linear equations, and the FOIL method for multiplying more than one variable. So, come next time and we'll see how to FOIL even more complicated algebraic expressions. Thank you.